Good morning. My name is Marian Morris. My colleagues and I appreciate the opportunity to share with you our presentation as part of the SPWLA The More You Know series. We are also grateful to SPWLA and in particular to Katerina for her assistance and patience helping us to prepare the pre-recorded materials. The focus of our presentation today are the applications of PetroMar's modular suite of LWD tools. The suite consists of three tools: FracView, high-resolution borehole imager; SpectraView, spectral and azimuthal gamma ray tool; and DrillView, an advanced drilling dynamics tool. When architecting the suite, we focused on several key factors. Number one, we chose measurements that bring value to multiple workflows. Number two, measurements that are particularly well suited for unconventional resources, but apply to conventional workflows as well. And number three, designs that can operate in any mud, water-based, oil-based, and in any borehole, horizontal, vertical. Let's review the key characteristics of the three tools in our portfolio, as well as the deliverables. FracView, in addition to acquiring borehole images that are actually acquired by two back-to-back ultrasonic transducers, also measures very precise caliper. From that caliper, borehole shape and quality is derived. Continuous inclination and drilling dynamics package complement the suite of measurement. SpectraView, a spectral and azimuthal gamma ray tool, in addition to acquiring a standard gamma ray measurement, API calibrated, also produces directional gamma ray images, as well as potassium, uranium, and thorium concentrations derived from gamma ray spectra. Those concentrations can be used for clay typing or total organic content characterization. DrillView acquires a comprehensive suite of drilling dynamics measurements, starting with weight on bit, torque on bit, and bending on bit, as well as bending azimuth. Those measurements are very carefully resolved such that weight doesn't propagate into torque or vice versa. Also, pressure effects are carefully compensated. Two pressures are acquired by DrillView, annulus and mudflow, as well as 4-axis accelerations that include among them the high-frequency torsional acceleration. High-frequency RPM is derived from both magnetometers and gyro, and BHA motion is derived from all of the drilling dynamics measurements. That BHA motion shows us the trajectory of the BHA, the direction, magnitude, and frequency of the whirl. As you can see, this LWD tool suite provides a wealth of data, wealth of measurements, and those measurements, as my colleagues will demonstrate later, fit many workflows that range from understanding of the reservoir, for example, the bedding, dips, and strikes from borehole images, fracture analysis and modeling from the fractures detected by FracView, risk mitigation by, for example, using information about faults that FracView can see. Rock geomechanics applications are supported by all three tools. FracView borehole shape for breakouts analysis feeds that model. The clay typing from SpectraView can contribute to that. DrillView providing calculations of MSC and high frequency drilling dynamics can help in characterizations of geomechanical properties of the rock. Borehole placement and completions are effectively fed by many of those, including fracture and formation, understanding of properties of the formation. Drilling performance optimization can be accomplished by using DrillView data for example, characterization and mitigation of drilling dysfunction, as well as borehole quality improvement. Formation integrity testing and underbalance drilling are other applications that may benefit from this data. Let's discuss briefly the common characteristics of all PetroMar tools. Those tools are memory only and are service provider agnostic. That means they can operate on any BHA regardless of the providers of other services. They're very compact and easy to deploy, typically 5 to 6 feet long, very robust. FracView, for example, is qualified for high pressure, high temperature operation, including offshore. The tools can operate in any combination on the same BHA, also combinable with third-party tools. FracView and SpectraView are available in 4 3/4 and 6 3/4 tool sizes. DrillView is available in 6 3/4 tool size. The tools are self-contained, battery-operated, with very long recording times in excess of 200 hours. Bottom line, because of their compact size, ease of deployment, and robustness, they are a very economical way to acquire valuable data set. Now let me pass the presentation to my colleague, Tollef Winslow, who will describe in more detail applications of FracView.
Okay, thank you, Marian. FracView is a ultrasonic borehole imager, borehole caliper, as well as high-frequency drilling dynamic monitor, all wrapped up into one 5-foot sub. What it can give you, by the time you add all these measurements together, is besides the borehole images and the caliper, both of which derive from the ultrasonic sensors which are located on either opposite sides of the tool, it also gives you instantaneous tool face, so you know which direction your bit is pointed. So instantaneous RPM, so you know instantaneously how fast your BHA is turning, BHA motion, whirl, continuous inclination, and micro dogleg severity. You put all that together and you have a pretty good picture of what's going on downhole. So the output as it comes out is an image with 1/4" resolution. And of course, every borehole is round, and to display that, we take and split the borehole on the high side, in this case, for a lateral. So imagine you took a tube and you just took a razor and you slit it down the top, and then you laid it open. That's exactly what you're seeing here on this image on the right, is you have the high side on the left and the right, and the bottom of the borehole's in the middle. So that nice fracture that you see for 1/3, sinusoid is at the top, and then it goes down just a little bit. And then at the bottom, you have a little bit of parallels to the bedding. So how do you get all these nice images? We deliver them both as a DLIST file because they are so large. LAS does not work in a PDF. And if needed, we can also assist with the interpretation.
Thanks, Tollef. When looking at the analysis of these images, there are a whole series of ways we can look at them. And we can undertake the type of analysis of these images that we could from any other borehole image. And so basically what we're able to do is we can undertake structural analysis, we can look at fractures, we can classify those fractures into different types, and that's basically what you're seeing in the image there on the right, where we have different colors representing different fracture types, mostly the blues and the purples, plus our bedding, which is in red. In addition to that, we can see the dip of our bedding, we can identify faults and conformities. We can also look at sedimentary structures and any of the heterogeneities that we would expect to see in the formation. We'll also be able to measure formation stress where we have either breakout or induced fracturing, and have a look at where we may have stress rotation. We can look at fold axes and the relationships between fractures and bedding. This also gives us significant input into 2-dimensional, 3-dimensional structural analyses. So our near wellbore model can fit into a customer's more developed structural model that's perhaps field-wide or even basin-wide. We also provide data that can be put into data-driven seismic interpretations as well. So in terms of completion optimization and reduction of risk, we also have the ability to look at wellbore stability, identifying where we have faults, what the associated damage zones of those faults are, etc. And also looking for things like thief zone detection, where we may have cross-well communication between, particularly between lateral wells, and looking at things like pressurized mudcap drilling. In terms of the drilling dysfunction, we'll be looking at things like stick slip, whirl, borehole spirality, and how these things interact with the geology as well. Can we see reasons there for some of the effects that we actually see? In this case, what we have is an example of some real data from a West Texas operator who wanted to evaluate the location and orientation of subseismic faults in order so that they could optimize the planning of future well paths and actually provide a key input into risk mitigation and their completion design. So basically what we were trying to do here was to identify the positions, the orientations, and the nature of all of these largely subseismic faults in a lateral well. So our solution to this was to use our FracView images to actually visualize where these major and minor fault zones were, to actually identify the positions of those faults and look at the nature of them. We would use our images to analyze the image features, the dip changes, anything related to drag zones, and then to tabulate all of those depth-related results for all of the faults that were intersected by that wellbore. Our acoustic log interpretation was integrated with regional seismic volume and allowed us to flag critical intervals and facilitated an improved drilling process and in reducing that risk. The geological model then allows, from the individual image here, then allows to update that the larger geological model and allow the customer to optimize future well paths at that landing zone within the Delaware Basin. So this type of analysis is key to input to minimizing wellbore failure potential and the optimization of the completion design. So our value proposition for something like this is a good understanding of fault locations. The significance helps minimize the risk of damage or even complete wellbore failure. The analysis, along with the evaluation of the fault orientations, also allows essential optimization of that completion design, the stage spacing, and the cluster lengths.
So this is another example, a bit different application from what Andy was showing before. In this case, one of the key factors to improve productivity of any well in any unconventional reservoir is the optimal orientation of the well path. So the idea is to have a well that is oriented almost 90 degrees to the maximum horizontal stress, which will allow the better production, easier drilling, and more stable boreholes. So that is all in a benefit of the bottom line of the cost of the well and the return of investment. A well that is not located almost perpendicular to the maximum horizontal stress, like the example in the back end, was 45 degrees. We still get fractures and develop through the fracking process, but they are not all the same length, and the volume of rock that is stimulated is much less than the optimal orientation. These type of features are normally identified from vertical wells, where if the mud is too heavy, we will see drilling-induced fractures. Or if the mud is too light, we will have breakouts like on the well B on the image. So that orientation. These azimuths give us the orientation of the stresses, the in situ stresses that control the fracture process in a lateral. In this case, the effect could be up to 50% of production at the end because of the optimal well orientation. Other of the applications is the caliper image that we create, what we can generate from this tool. As being as an ultrasonic, what is being used is the transit time, the time that the sound goes through the mud system and comes back from the borehole. So that generates a 360 degrees image that also covers the same resolution as the geologic image. And from that, we can generate eight different diameters that basically are the calipers, symmetrically oriented, and any variation of the borehole diameter is recorded from this data as well, the 360 degrees image. The image what we see on the right side shows some diagonal shadows, brown zones. These are basically borehole spirals, and the borehole spiraling is something that can affect the running casing and cementing process. So the borehole condition is very important to actually see any of these issues while drilling or after drilling. Also on the curves on the bottom, we can see that when all the 8 diameters overlay perfectly, the borehole is round, but that doesn't mean that this is rugosity free. So we can see that it's wiggling around. But there is one section where the borehole was heavily enlarged and the curves are separating. So the diameter of the borehole is not ideal, it's not constant, and also it's largely enlarged. In this scale, I mean, that's we can show that 5 divisions is 1 inch. So there we can see the actual resolution and the details that we can see from the caliper image, which has a precision of 0.2 of an inch when the borehole is in ideal conditions. Also, we get continuous inclination, which is one of the key factors to identify micro doglegs in the process of drilling, which at the end will affect all the drilling process, the casing running, and cementing as well.
Thank you, man. And there's always the question, how good is your caliper? And so, you know, because most of the time we're used to in the drilling industry having these arms that come out from a wireline tool to give us a caliper, you know, and that's mechanical. We trust things that are mechanical. So we ran this experiment with the tool. You know, we drilled one section down, and then while rotating, we back reamed over that same exact section. And so we've got at the top, we've got the 2 caliper images in the cylinder. We've got a tadpoles above that. But then below that, we've got the caliper repeated, and then the caliper. And then we've got a copy of the image. And now here's where it gets interesting. You've also got your micro dogleg severities, your continuous inclination, the orientation, and some drilling data. But now where it's really interesting is the third one from the bottom. In green, you've got your initial caliper, and in red, you've got your repeat caliper. And notice that they almost perfectly overlay. There's a couple of spots where it's just a hair bit different, and that's probably because of a little bit more breakout in that area after drilling. But this was a really nice wellbore. It stayed together. They were doing a really good job drilling, managing their mud weights, and that we were able to get a really nice repeat image. Now, of course, if you're not getting a repeat image, now you know that, or repeat caliper, and you know that you have changes in your wellbore, and you can actually use that as a time-lapse photograph, so to speak, to see what is actually happening to my wellbore. I start to do some analysis with both the caliper and the image, how the wellbore degrades over time.
Okay, so to summarize, the next tool is our spectral gamma ray, Azimuthal spectral gamma ray, which delivers, of course, a full API calibrated gamma ray, total gamma ray, and also it's directional. So because we have the orientation system integrated with the tool as well. So we can provide the energy spectrum of the elements of the isotopes and the concentrations of potassium, uranium, and thorium. So that gives the full spectral output that any wireline tool can do, but in while drilling. Of course, the applications are very well known. This is not a new tool. This is not new technology. So the lithology determinations like sand shales, minerals that are accessory, or carbonate formations to distinguish limestones and dolomites and so on. Of course, the unconformity detections, some correlations, well correlations, phase zones, cross-well communications if we have tracers in the well, or then the type of shale can give us brittleness or if it's not more ductile. The correlation of uranium with TOC can give us also the best zones in unconventionals for the source rock. And in general, because it's an oriented image, then we can calculate structural depth as the tool has a image resolution about 6 to 12 inches. Using the typical cross plot, we can define the type of clays that we might find in the lithologies. And of course, using the uranium contact, we can correlate with TOC as in the triangular cross plot. So here's an example of the output of the tool, where we have the general recording of temperatures and the time during recording. Of course, the gamma ray, the total gamma ray API curve. Then we have the content of thorium, uranium, potassium. That gives us the relative amounts of each of the elements. And then the acquisition time, which is very important because the time that our sensors are exposed to the radiation also is the amount of counts that we get, and that can influence the output of the tool, of the measurement itself. So that is very important when the tool is rotating, and how fast is it rotating and how fast is it moving along the borehole. Then we have the curves for the three elements, concentrations, the RPM, as I said, is very important with the time, vibration, shock, all those are drilling dynamics parameters that can influence the measurement. But in general, this tool has been calibrated and is very stable in the measurement and accurate. In the next one, we can see a comparison of different ROPs, where we can see how the variations are on the measurement itself. For the total gamma ray, the red curve is 150 feet an hour. The blue curve is between 30 and 60 feet an hour. And of course, the total gamma ray is almost identical, where we have some variations in the potassium curve, which follows the trend with different resolution, because the faster we drill is less resolution. Uranium is almost identical. It's very good, very correlational. Thorium is also a bit affected, but not much. So even fast drilling will not change dramatically any response for any of the measurements of the concentrations of the elements. And at the bottom, we can see the correlation with ROP. So from fast or slow, and where there were changes in the speed of drilling on the progression of the drill process. And we can see that it's very, very reliable in that sense.
Let's look a little closer at the DrillView Drilling Conditions Monitor. It's a compact tool, approximately 5 feet long, with a slick 2¼ inch mud flow channel. The measurements that the tool acquires and the tool deliverables include drilling forces, weight, torque, and bending moment, 2 pressures from the annulus and mud flow channel, very wide band accelerations. This is one of the distinguishing features of DrillView. Its sensors are capable of pretty wide bandwidth, 5 kHz sensor bandwidth on all 4 axes, and up to 20 kHz sampling with proper filtering, so we don't have aliasing, as well as mounting of the sensors such that mounting resonances do not play a role in this measurement. The BHA motion is derived from the drilling dynamics measurements. Instantaneous tool phase and RPM are calculated from both magnetometers and gyro. The BHA trajectory, including whirl, is also calculated. So we can see the whirl's magnitude, direction, and frequency. Continuous survey and micro doglegs calculated from those continuous surveys are also provided. We typically bundle the available surface data with the DrillView acquisition, and the logs are delivered in both DLIS and PDF formats. We also offer interpretation, both DrillView data standalone or in conjunction with the available surface data and other logs. The illustration to the right is an example of a drilling dysfunction. That is one of those features that you can see with DrillView. On top, from the top, we see acceleration on track number 1, the topmost track, followed by magnetic tool phase on track number 2, surface and downhole RPM on track number 3, and track number 4 on the bottom is the ROP. In this case, we look at a drilling dysfunction, a stick slip event that occurs at the connection of the pipe when weight was removed from the bit. The BHA went into a stick mode. Then at some point, when the weight is taken off completely from the bit, the BHA goes into very rapid slip with RPM exceeding 500 at its peak. And eventually, when the bit is engaged, the BHA starts rotating again. This is just one example of what you can see. We don't have enough time to show more complex examples. Let's talk briefly about DrillView applications. Those range from drilling dysfunction mitigation, stick slip, whirl, characterization and mitigation of friction and drag, especially if we have multiple tools in measurement along string mode. Verification and calibration of drilling dynamics models is a common application of this kind of data. Derivation of geomechanical properties of the rock, both from the vibration and also in conjunction with the spectral gamma ray data. Forensics of mud motor and bits. Applications of pressure measurements are shown on the right side. Let's keep in mind that those are not real-time measurements. Those are memory mode measurements, so the learning is applied on the next job. Now let me pass the presentation back to Andy, who will talk about PetroMar's interpretation capabilities.
So here we're going to talk about our interpretation capabilities, and as well as our standard analysis that would include things like looking at bedding inclination, bedding attitude. We can look at the different fracture typing, look at the fracture orientation, And this image on the right also shows that we can look at the fracture density along the hole, looking at how that fracture density varies, and also to correct, particularly where we've got more than one fracture set, we can do a correction for the downhole attitude of those fractures to correct for how many of each fracture types are actually seen to try and correct for the borehole bias that's created there. So our advanced interpretation techniques would be to take this also to the next level, to integrate it with different data sets. For example, spectral and azimuthal gamma ray interpretation. And you can see we actually have some uranium, potassium, thorium information in this particular log. In this case, not from our own tool, but this is actually taken from cuttings analysis. So we can integrate with any other type of information, open hole logs, the drilling dynamics data that we've been discussing as well, and also to give joint interpretation of FracView, SpectraView, DrillView logs in association with any other third-party information such as mud logs, surface drilling data, third-party logs such as triple combo, quad combo, etc., sonic data, and also to integrate it with seismic data as well.